Hi and welcome to this video on linear equations and their graphs, and in this particular case, piecewise functions. You're going to really love this topic. So piecewise functions. Now you've dealt with linear functions before, and you've dealt maybe with some other functions as well. This course is primarily based on linear functions, but we could do piecewise functions with any type of function, curves, quadratics, etc. But for now we're just worried about linear functions. And what I'm going to show you is how we can combine two functions to set up one contextual situation. So there might be one situation where something changes after a certain amount of time or a certain number of whatever x is, maybe the number of apples you bought or whatever. Okay, so we have a piecewise function example here. We have our standard y equals, and then we've got this funny old curly bracket here, and that curly bracket represents that there is more than one thing involved in this particular function. There's a breakup. Maybe there's 2, maybe there's 3, maybe there's 10. In this case we've got 2. So we've got a function here for all the x values between 0 and 3, it's 2x. And then we have another function here that's different for all the x values between 3 and 10. Now you notice 3 is included in the first one, less than or equal to, but not included in the second one, which is good because we don't want some number included in both. The second thing you'll notice here is that this could be discrete or it could be continuous data. So discrete data is countable. So it could just be 0, 1, 2 and 3 here, but it could also be continuous, which is measurable. So it could be 0, 0.1, 0.2 all the way up to 2.99 or whatever. But that doesn't matter, and it may matter when the context comes, but for now we're just looking at the maths. So what I do first is sketch my axes, and I recognise here that I've got y and I've got x, and of course I'm going on the x-axis from 3 to 10, I'm going to throw 10 up here. And on the y-axis, I'm going up to, well, I don't quite know, so I need to work it out. Now, this is a positive gradient 2, positive gradient 1, so it's an always increasing function that way. So with that in mind, I think I might just look at what happens at x equals 10. That should represent my highest point, but I need to be a bit careful. So x equals 10, I get 10 plus 3 is 13. X equals 3, the upper point of the first function is 6, so 13 is probably going to be my upper point. So I'll just pop a 10 there. And 13 is just above that. 10 is a nice number to scale, 13 is not a nice number to scale. Okay, so what I'm going to do to sketch my function is I'm going to mark the important coordinates, and that is the start and end. So the first important coordinate here is 0. When x is 0, y is 0. So that's right here. And I'll mark that as 0, 0. My second important point is at 3, that's the end. And 2 times 3 is 6, so when x is 3, y is 6, which is about there. So I get 3, 6. Then, when I put it into this one, I start at 3, so 3 plus 3 is 6, so the next one starts there, but of course, I've got a circle, I'll explain that in a minute. And then when x is 10, I get 13 as we calculated before, so 10 goes up to 13, which is here, and I can mark the point 10, 13. And then I just connect them. So this connects to there, and this one connects to there. Now there's a couple of important points here. This is a way of representing the fact that when x is equal to 3, it's connected to the first line. So 3 is there, but not at the dot for the second line. The second line is greater than 3 but not equal to. So I've got a circle to represent that. And that's one way of doing that. Some contexts will be important and some it won't. But other than that, here's our key components to drawing a piecewise function. The only other piece of information, which is a piece of vocabulary I mentioned to you, is the fact that this is a continuous piecewise function. So it meets and departs at the same point. You could have a function that goes up to here and then the second part starts here and goes up. That would also be a piecewise function, but because of this it would be discontinuous. And that situation might be a costing situation where if you buy 0 to 3 things, it costs this much, it's graduating. But then when you get to 3, all of a sudden there's an additional surcharge. Maybe you need to hire another vehicle to move things or something. That's added on instantly and it moves up. And there are some contexts where you can't have that jump. So most of the time you're going to have continuous, sometimes you won't. Just be thoughtful about that. Let's have a look at an example. Okay, So in this example, we're looking at the cost of hiring a removalist company, and we need to work out the difference between 6 hours and 10 hours. Now we'll note, before we sketch the function, we could do this using the functions here, that's those continuous piecewise functions for costing. But I'm going to draw the function first because the question specifically states I need to do that, and then once we've sketched it, we'll do some calculations. So let's sketch it first of all. It is an increasing function. Makes sense to be an increasing function because costs wouldn't go down for a certain amount. And so we have the time that it's hired for and the cost of hiring this company. Starting with, t goes up to 8. So I'll put 8 here. I'll say 10 is about there. So we've got a little bit of space to go over. And at 8, 50 times 8 is 400 plus 280 is 680, but that's at the bottom end of our time scale here. So I'm going to go up to about 12, and we'll just have a look at what it is at 12. So at 12, t equals 12, 50 times 12 is 600, plus 280 is 880. So I'm just looking at how high my costing scale has to go to ensure I can fit my graph on. So at 12 I get up to 880, so I'll pop that about there, 12, 880. And now I'm going to backwards sketch, and I'm going to have this scale go up to about 1,000, which is a nice number to have on a scale. So let's backwards design this a little bit, and we'll do the next parts in pink. So first of all, it costs 200 for 0 to 2 hours. So 2 is about here, and 200 is about here. And it starts at 200, and it costs 200 the whole way. This is a flat graph. It's a flat cost, which makes sense, because a removalist company is not going to want to charge you $3 for 2 minutes of work. It's going to cost them a lot to set up the truck, bring it out, etc. So a flat rate, it's going to cost you $200 irrespective, and then it builds after 2 hours. Now we've got above 2 up to 8. So I'll just check there's no jump here. T equals 2. 80 times 2 is 160, plus 40 is 200. So there's no jump, but it does have that circle around it. And at 8 times 80 is 640, plus 40 is 680. And so at 8, which is here, I go up to about 680, which is about there. 8, 680. And of course I can sketch this now, and then I can sketch this. And then I've got this other one here, which should go from there to there if it's continuous. 50 times 8 is 400, plus 280 is, of course, again, 680. So there's my piecewise function. Now I could do some work on this piecewise function, particularly if I sketched it neatly to answer my question, and the question being, what is the difference between time of 6 hours and 10 hours? Well, 6 is here. That went a bit skew, it looks more like 5 now, but anyway, it's bent. And it's here. Now I don't know what that is, so let's say it's about 550, I don't know. And then 10 is here. And I take that along, it's more than 680. Let's say it's 750, for example. I can work out the difference is 200. Hopefully your graph is a little bit neater than mine, because I've just done this for the purpose of the video. The good thing here is that if you don't need a neat graph, you could do it algebraically as well. So we start by substituting and finding the cost at 6 hours. And the cost at 6 hours is we find the section where 6 exists, and that is here. And we put 6 into the function. So 80 times 6 plus 40 is equal to 480 plus 40, which is 520. Not a bad little estimate there. And then we can find the cost at 10 as well. So 10 is in this component. And 50 times 10 plus 280 is equal to 500 plus 280, which is 780. So they're both measured in dollars. And then our cost difference is the cost of 10 minus the cost of 6, which I write as difference. That's what I'm trying to calculate. That's equal to 780 minus 520, which is $260. So we can calculate the cost difference algebraically as well. It's going to be more accurate than my graph, but if you were asked to do it in an exam and calculate the cost difference on your graph and you've got some grid paper, well, let's make sure that we're accurate so you can do that really nicely. Otherwise, that's piecewise functions. All the best. Well, thanks for watching. I hope you enjoyed it as much as I enjoyed speaking about it.